Hello, my name is Johnny McClintock. Just a little bit about AntennaWare. We were founded in 2020, built on 2 decades of world-leading research in antennas and propagation on difficult platforms in challenging wireless communication environments. Today, we're going to run this webinar on best practice for designing for antennas. And we hope that by the end of the session, the key takeaways will be how to overcome antenna and propagation challenges for wearables, how to improve your wireless wearable testing, what performance could be achieved from wearables. We've got 2 speakers. We've got Dr. Gareth Conway, who's the CEO and co-founder of AntennaWare, and Dr. Matt Magill, who is the CTO and co-founder of AntennaWare. Just in terms of some housekeeping, we would encourage people to put in questions. This session should run for 35 to 40 minutes, and then we'll do a Q&A session. If you have questions, please put them in via the Q&A function at the bottom in the Zoom screen. And with that, I'm going to hand over to my colleague, Dr. Gareth Conway.
Thanks, Johnny. So this is AntennaWare's first webinar, certainly my first time doing something like this. So we created a few topics which we hope you get something out of. The first topic that I'm going to talk about is wireless is the weakest link for wearables. And that's largely sort of based on the research we've conducted before the company since 2005. I'll also then cover antennas and the human morphology. So that's a bit of a deeper dive into what the human morphology does to antennas. In the third section, I look at wearable measurements and test beds. So looking at what we have done to sort of isolate those antennas and the test beds we created to compare them. I'll finish then with antenna tips to overcome the human body. So some things I've learned over the years. I will then hand over to my colleague, Matt Magill, and he will show you what good looks like. For sometimes it's hard to, when you look at antennas, what's the art of possible. So when we look at wearables and we look at the applications, they're fairly broad as the human body is one of the biggest applications for wireless technology and certainly a growing application. The ones that I was primarily interested in research were those where it's very close fitting to the body, and that's really for the healthcare applications where you have some sort of sensor and you want it really close to the body because you have to pick up that vitals. Other applications, certainly the early adopters, will be the likes of your audio applications, mass market audio consumer applications, and then you can see the sport and rehabilitation applications there for more or less for tracking and just your general health awareness. The human body is a difficult platform, and what we also see is large-scale applications in industry, sensing, and difficult platforms. And that's really what we're looking at here in this webinar is difficult platforms. If I start to look at the wireless trends, certainly one of the biggest frequency bands of interest are unlicensed bands. So we see a lot of devices, and I'm sure people on this webinar would have seen that in Bluetooth, and that's really centered around the 2.45 gigahertz ISM band. You can see in your own homes a lot of applications in 5.8 gigahertz, and they're interoperable and popular with OEMs developing solutions. What we also then see forward-looking is a move to go down in frequency to get better range, certainly for widely distributed sensing in IoT. So they're starting to utilize the DEC band, which is at 1.9 gigahertz, and they've always used stuff sub-gigahertz. There has been a trend to go up for performance quality for size, speed, power, data, up into the UWB band. It's not a new band. It's been around for a very long time, but it's certainly with the likes of Apple releasing silicon, Samsung last year releasing their own proprietary silicon, we're seeing a lot more applications in the UWB band. So that's where I sort of see wearables and their frequency operation. The problem that we're trying to address, the difficult platforms and the human body being that difficult platform, is generally around limited wireless coverage, reliability, data dropouts. What we want to see, and certainly what the solution should be, is more complete coverage. So what we're trying to avoid is that sort of shadow zone at the back of the platform. And that platform could be the human body, which is the focus of this webinar, or it could be any conductive medium like metal. When I sort of think about the performance and the wireless coverage, we can dive a bit deeper in and explore poor radiation efficiency, impedance detuning, and absorption, which all bundle together to give us limited wireless coverage. Using full wave numerical EM solvers and looking at cross sections of the human body, if we took a cross section of the torso region, we can put a device on the back of that body and visualize the electromagnetic fields flowing around the surface. So in this figure, you can see like a hot region, white sort of region where the source is, like the antenna is placed on the back of the torso. And if we could see it in free space, you could see the waves creeping around. And what we get is a poor region at the front of that human body. We call that the blocked shadow zone. We call the term body blocking. So this could be for a wearable, sport, healthcare, or any sort of hearable device. It could be the same, it'll give you the same features when you mount it on the head. When we look at how people have tried to solve this in the past, they've turned up the transmit powers, maximized them. They've maybe put in front-end amplification, or maybe tried to put in some antenna diversity. Obviously, more antennas, more power equals less battery life, which we know for wearables, the size of the battery, the power usage is critical. This comes at a cost. Some people will put multiple devices on the body, like a device on each ear and the head, and doing that to try and solve a problem doubles your BOM cost. There is a hard limit on how much power you can put in to try and solve this problem because of SAR regulations and energy conservation. We don't want to put a lot of energy into a specific local spot on the human body. So what we were looking for in the research is certainly a more elegant way of doing this from one device placed on the body without having to introduce wearable devices with a huge infrastructure around the body so that there is no shadow zone. It always has got a line of sight link. That limits the deployability, the cost of infrastructure, not really a solution to the problem of better performance from a wearable. If we look at E-field sections or cross sections of the fields radiating out from a typical antenna on the body, here's what we want to see. On the left, we've got an antenna radiating across if we're looking down on the antenna or down on the human body, we can see that we're getting that body blocking as the waves creep around. So that's in that dark region at the back, that's where the signal is going to drop out. If we look at the right, that's what we want to achieve. We want to achieve is we still get some attenuation around the body. That's the physics, the propagation. You can't do anything there. What we want to do is get more signal coverage around the human body. So let's take a closer look at the human body and the morphology with respect to antennas. If we look at it, I think this is in most books, if you take general antenna characteristics, when we were doing the pre-work in antenna analysis and propagation, we were interested in certain quantities. Basically, what I was primarily focused on is antenna impedance in terms of circuit quantities, the match, the return loss. In terms of space quantities, I was looking at the radiation characteristics, that's like your field pattern, your polarization, power patterns, directivity, gain. From that, there's really about 4 key things, characteristics or metrics that I'd like to measure when I'm looking at wearables. One being impedance detuning, the second being radiation pattern and radiation efficiency, and then of course the absorption, which is linked to radiation efficiency. So where is it efficient? Is it efficient in the right directions? Is it efficient where we need it? For example, in that shadow zone. In terms of the propagation, we can learn a lot from the far field analysis, but it doesn't help us a lot when we start to design antennas that are closer to the human body. And when I say closer, what I mean is about a quarter wavelength from the human body. So we're not in the far field zone where most analysis is completed for antennas. We're in that near field reactive zone. So about lambda over 2 pi, about usually if I was looking at this, I wouldn't consider anything past a quarter of a wavelength from the tissue as a wearable or a close fitting wearable device. So I'm looking at something, if we think around 2.5 gigahertz, I'm looking for something within a 30 millimeter spacing from the human body. Obviously, the closer we get to that body, the more difficult things get. So it's this little red region that I've highlighted here, very close to the source in the reactive near field region, where the equations, the analysis gets a lot more difficult, where we really need to get the performance gains in terms of coupling and how the antenna sees the human body. We need to get that right. That's where the most bang for buck is. So looking at the human tissue and what's of interest when we look at human tissue is the electrical characteristics of that tissue. These are primarily your ER, your relative permittivity, and your conductivity in Siemens per meter. The table at the top shows different types of tissue. In this case, I've selected muscle, skin, bone, and fat. On Darren on the left, we have the frequency. So we're looking really to understand, as we go up in frequency, what are the characteristics of muscle, skin, bone, fat going to do to the properties of the media that we're mounting the antenna on. There are generally two groups of tissue. One is muscle tissue, or one is high water content tissue, which is your muscle and skin. The other is low water content tissue, such as bone and fat or subcutaneous adipose tissue, SAT tissue. If you look at the figure on the right, you can see that if we take a cross section of skin with the epidermis layer and the subcutaneous adipose tissue, it's fairly complex. It's not just a simple homogeneous block of tissue. Below that figure, we have far field and plane wave attenuations on the tissue, which don't really do a lot for us when in that reactive near field, but it does give us an indication of sort of the attenuation of that tissue. For example, 40 dB per centimeter for some layers at 2.5 gigahertz. If we look at the figure on the bottom left, the colored chart, 3D chart, and we look at the attenuation up the vertical axis, we can see that as the conductivity rises, the attenuation rises. So really the parameter of interest for us when we look at the human body is the conductivity of the tissue. That creates the loss, that creates the absorption. It's a conductive layer, and it creates the coupling from the antenna. When I think about the human body, and if you want to forget about all the physics and the electromagnetics behind it, it's just like a big, wet, salty sponge. And there only is one SpongeBob, but you have to think of this as that everybody's got a different hydration, everybody's going to have a different salt content. That could vary from day to day. So it's really a complex structure that we're trying to match an antenna to. And we did do the analysis. We started to look at different people. So looking at 50 different live subjects, we put them in a reverberation chamber. We got 4 or 5 different antennas. We tested on them. We put them, spun them around for a half an hour each, and we took the return loss and radiation efficiency measurements for those people. What we did notice is that for any antenna, which was shown here, and the frequencies of interest for us at that time were 868 megahertz and 2.45 gigahertz. You can see that it's highly variable. So you can't just test on 1 or 2 people in the lab and think your product's going to work out there in real deployment. And this is only 50 people, it's not the whole population, but it's certainly a lot closer and a fairly rigorous measurement campaign in order to understand this. Essentially, the takeaway message here is that you do not want your product performance to look like this in terms of its antenna characteristics. What we were looking to achieve with the research was something that had a single resonant frequency, or at least a predictable efficiency on different platforms so that we could have confidence and reliability in deploying something that would work on any platform. What is good about the industry, certainly, I'm not sure what the date on this was, but what came out from Fractus was that they now understood that when you put antennas next to a typical platform and some of their antennas were getting used in wearable devices, that it didn't give the performance that they had on their data sheet at free space. So this was a positive thing coming out from Fractus, where they published the information on their antenna, albeit beside a head. What you can see, and I agreed with the research study that I completed, was that you can see variations in VSWR and certainly a huge variation in efficiency across those platforms. And basically, what you can derive from that is that a lot of commercial off-the-shelf antennas are designed for free space, which is great, but they were not wearable antennas, never designed to be put close to a typical platform. So some of the questions I asked myself was, how can I be confident my antennas are any better than the ones that are out there at the minute that I find in wearables? When I worked with some commercial companies in my time, they were asking me, how do we know our antennas are going to work? So how does the industry know that the antenna will work on everybody? And that's impossible to test. If you're a system design engineer, it's impossible to test on everybody and be sure that somebody with a certain tissue topology doesn't destroy your communications. How can we compare designs when there's no standardized approach? So we're on to wearable measurement test beds, and this is really built to standardize the approach. So we've, over the last 2 decades, conducted a lot of wearable measurements. We looked at indoors, we looked at outdoors, we looked at user effects, we looked at the signal analysis, we looked at statistically trying to predict it. And you can see that in a multipath environment, the signal bounces around. So it's very hard to, if you sort of look at multipath and look at your received signal, it's very hard to repeat that test in typical environments. If I walked into the same environment and tried to walk the same path, I'd probably get a different result. So we were looking at antennas and propagation at that point, and there's not really much you can do about the propagation. You can't control the environment your device will be deployed in. So I wanted to be able to de-embed the antenna. I wanted to be able to look closely at the antenna and see, can we improve the antenna in order to improve the propagation? So the bottom left looks at different effects, people walking, non-line of sight. You can see that even just for one person, that receives signal strength with the fades in it is pretty messy. And if you start to analyze that and look at the fading, you could maybe experience fades, but certainly in the region of 10 to 30 dB, which is massive. When we look at wearable measurements, if you put 2 devices on the same body and you point those 2 bodies towards each other, you get a reasonable signal level. But if you sort of look around time at 5 seconds, as soon as those bodies turn around and they're both in that non-line of sight region, the signal drops right close to the noise floor, below minus 90 dBm. As they turn around again, the signal goes up. It's really that 5-second point where they turned around that you're not getting any communication, and that's the problem case that we want to address. So in terms of measurement challenges, the research we conducted shows that consistent and reliable performance is achieved when the antenna supports on-body propagation modes. So I wanted to isolate the on-body propagation mode and design an antenna that would maximize it for me. So to do that, there's a measurement challenge, and that's where we have to test for worst case. To do that, we have to isolate that on-body propagation mode, and to isolate it, we need to put it into anechoic environments, so no multipath, so we can repeatedly test it. We also need to then compare the antennas on repeatable test beds. We want to minimize the cable radiation effects for printed and chip antennas because we know that they are problematic. In terms of antenna and propagation challenges, what I wanted from the antenna was, or the challenge is resonant frequency detuning. What I wanted was stable impedance or stable S11. The other challenge is radiation efficiency reduction. What I wanted to do is minimize the power radiated and absorbed by the tissue. Really, the crux of the problem is this body shadowing in non-line of sight. So I wanted to be able to control the propagation from the solution. And the other interesting one is device regulatory. So you've got specific absorption rates, which you have to adhere to in the IRP. And what I wanted to do there was provide uniform radiation pattern, omnidirectional from a wearable. So we've done the applied research. We generated the concepts. We've done the EM analysis. We put multiple devices on close-fitting garments on people. We then used that analysis to try and derive what would be best representative platform to test these on. So we were interested in not only in on-body propagation, off-body propagation, but into-body propagation. We done full scans of the human body, autonomically correct models, looked at the propagation, and we come up with this cubical cylinder that we developed in-house because it didn't exist on the market. So testbed development comprised of skin, subcutaneous adipose tissue, muscle, so it was more representative of homogeneous phantoms. We mixed up the materials ourselves and developed a solid testbed for our analysis for to look at and isolate this worst case. To do this, we had to match the Gabriel tissue properties of different tissues. So we had muscle, skin, subcutaneous adipose tissue for the tank and some insert layers. And we were able to do that within about 10% with our materials. So we were really primarily looking at conductivity, but also permittivity, so the electrical characteristics. We selected some commercial antennas off online, and we used them in our analysis. So we're looking at on-body propagation, typical chip antennas from the likes of Molex, Fractus, TI, which appear a lot on wearables, and TDK, etc. We put them in our reverb chamber on the test bed that we built, and we were able to analyze radiation efficiency within that. We then put it on anechoic chambers, able to analyze radiation characteristics within that, and we compared them to see just what was possible. And this, when we looked at it, we could see that it was 10 to 20 dB their performance gain compared to some antennas for typical scenarios. And we were able to stand by that and then try to develop antennas that matched that. In terms of the antennas and propagation measurements, we have learned how to produce this worst case scenario. So there is, certainly as we move up in frequency, this becomes more critical. We're looking to minimize multipath. We have ways of minimizing the cable effects, which are only relevant for some antennas that maybe don't have a ground plane. We're able to certainly, with a high level of confidence, produce that non-line of sight worst case scenario. So essentially, that's what we've learned to do over the years, and we can do it well, is isolating the weakest link in a clinical type environment where we can control everything. And that's really what you want to be designing for, is to not leave the antenna radiating in a way that it performs the weakest link, or at least test your system in its worst case, because that's really the benchmark for your performance. That's where the data is going to drop out, and that's where you're going to have most problems. Being able to do this on everybody, you're going to have to get an antenna that works well and is agnostic to human tissue or the platform you mount it on. So some quick do's and don'ts to overcome the human body. I've selected about 3 each. So in terms of antenna tips, don't use antennas that rely on a ground plane to radiate. We see a lot of with like keep out areas and things with chip type antennas. That's certainly not the way to start in our experience. Don't expect the chip antennas to do the radiation. It's so small, it's not really relevant to a fraction of a wavelength. Something else has to be doing some of the radiation, and you need to be careful around that. And don't design for best case. So don't test your system in a direct line of sight unless that's the only use case you're going to use it in, because you can bet your life that the non-line of sight case is where the product's going to fall over. In terms of do's, and we never see this as antenna engineers, is to start with the antenna and don't treat it as an afterthought. You can't do wireless without antennas. Second thing is select an antenna that is agnostic to what you put it on, and that may be even just the PCB, but also possibly the human body, so tissue, metal. And lastly, test and analyze for worst case in situ So be rigorous and understand its limitations for your application. I'm now going to hand you over to Dr. Matthew Magill, and like I said previously in the webinar, sometimes hard to know what good looks like and what is achievable in terms of wearables. So over to Matt.
Okay, thanks, Gareth. Okay, sorry about that. Yeah. So now I'm just going to talk about some of the work we do here at AntennaWare and how we measure our wearable antennas. So as we focus primarily on wearable antenna design, we do a lot of wearable measurements. We do these on a range of phantoms. So these can be just head phantoms, torso phantoms, full body, and then sometimes even putting people in chambers. We look at a range of frequencies, so this can be from sort of 400 megahertz up to 8 gigahertz. And, we use a range of equipment and chambers to do this. So we can use, reverberation chambers, as you've seen before, anechoic chambers, and these can be far-field and near-field probe, or near-field chambers, such as this near-field multi-probe anechoic chamber you can see in these pictures. So this is kind of, when we're doing the fundamental antenna research, this is probably the best place to be. Conducting these kind of passive antenna measurements or even OTA measurements in an anechoic environment, it lets us isolate the antenna performance from the effects of multipath. And this can really help us analyze and diagnose any antenna problems we're having or we expect to have. And we can also optimize antenna performance within devices for whatever application we're looking at. So as Gareth mentioned, there's probably three main challenges that we always try to overcome in our wearable antenna designs. These are, we want obviously impedance stability, radiation efficiency, consistency, and we want to get over this body blocking effect. So probably the first thing you're going to look at is the S11 performance of the antenna. This is done pretty simply. You can just use a DNA. But what's important to do is to look at the S11 in a range of body placements and also at a range of different spacings. So you can use row cell foam spacers just to control the distance. And then we can look at the S11 measurements in our band of interest to make sure we have a good impedance measurement or impedance performance and that we're getting enough energy into the antenna. So in this S11 plot in the bottom left, just for this example, you can see that we have going from free space right up to 5 millimeters from the surface of the body, and we're having a totally stable impedance performance. And that's obviously good. It removes this unpredictable performance that we don't want to see that can affect the total radiation efficiency. On the right here, this is a radiation efficiency measurement done using a reverberation chamber. And you can see a similar good performance. So going from free space to 5 millimeters from the surface of a phantom head, I believe this is, and we're only getting a reduction of 1.5 dB. So that means you're only ever going to see, basically in all applications this can be used, we're only going to see 1.5 dB of performance variation. And this is good because some antennas can be as low as minus 10 dB, for example. So this is those first two examples or challenges solved. The next thing is looking at probably the most challenging part, and that's the radiation pattern of the antenna mounted on the body. In this case, we're looking at measurements done on a head phantom, and doing these measurements, we can see the extent the body blocking has in 3D rather than just these 2D plots. So the 4 plots on the right are from the 3D radiation pattern of the antennas on the head, and we're just looking at the difference between one of our body wave antennas and a printed antenna in 2 planes primarily. So you can see from these top 2 3D radiation plots, we're looking down on the top of the head phantom, the XY plane, so you can see the coordinate system. And we can immediately see the impact the head has on a radiation pattern, especially if you only ever really look at radiation patterns in free space. This is much more pronounced on the printed monopole, with reduced gain seen in virtually all directions, especially in the X direction through the head, but not so much with the body wave antenna, as we aim to promote propagation around the head to address these non-line of sight issues. From the 2 bottom plots, we're looking at the head in the YZ plane from the shadowed side of the head. And here you can really see the difference between the two antennas, with the printed monopole suffering from shadowing much more than our body wave antenna. And while it's important to look at the 3D radiation pattern, it's also really useful to look at the classic 2D major cuts on a polar plot. And this is especially useful for comparison. So on this plot on the bottom left, we're looking at the XY plane total gain for both antennas on a polar plot. And here we can really see the benefits of this body wave propagation, especially under non-line of sight conditions. We can see that in some locations we're getting up to 15 dB increase in gain, shown using the body wave antenna. Now, I mean, it's fine to analyze antenna performance in anechoic chambers, but eventually you have to go into the real world. So a common approach is to use these small sort of battery operated test boards, and they usually have to be representative of the final product to go analyze the antenna performance when it's integrated into these. I mean, Gareth has mentioned this previously, but it's important because these products, they usually have ground planes smaller than the evaluation boards some antennas come on. And if the antenna you're testing primarily relies on that ground plane for good radiation performance, you can sometimes see very different performance when you go to your own product design. And if you're not careful and you've conducted tests with evaluation boards, the cables that you would use to connect the evaluation boards can radiate themselves, the air conductor of the cable. And this can actually, in some cases, contribute a lot of radiation, which you think you're actually seeing from the antenna. This is quite common with these low quality pigtail type connectors or cables you see for FL connectors and things like that. The problem then is that when you integrate the antenna into the PCB and the cable's not there anymore, you can see your expected antenna performance fall off quite a bit. So just in this case, this is an example of a test. Created sort of two small battery operated test boards, and we just get them to spit out packets at 2.4 gigahertz, and we're measuring the RSSI, so the received signal strength. This is quite a common approach, and there are different ways you can do this, like using spectrum analyzers, transmitting constant waves, things like that. But the important thing is you're using a test board representative of the final product. Again, notice I'm conducting this test outdoors. I mean, it's not quite anechoic, but there is much less multipath and interference when you're compared to an indoors lab, for example. So in this test, I'm essentially measuring the path loss around my body from chest to back. So we've got two pairs of devices, one with a body wave antenna and one with a printed antenna. The device on my back will be transmitting and the device on the chest receiving. And then we're relaying that measurement of the RSSI to an off-body receiver. So here's me, I'm awkwardly putting up my chest on my back, and then we're starting to transmit. So this is for the printed antenna. We can see, there's about, with the 0 dBm transmit power, about 90 dBm of loss. And then with the body wave antennas, we're at a signal strength of about minus 65 dBm. So that's quite an increase, and this is because of that propagation around the body that we were talking about earlier. And at minus 90 with these Bluetooth sort of system or SoCs, that's virtually in the noise floor, and you would suffer from dropouts. Whereas minus 65 is a much more stable signal strength. Similar kind of measurement that we've done. We've used the Silicon Labs Thunderboards, and we've integrated one with the standard chip antenna and one with the body wave antenna. So we're doing a similar kind of measurement. We're looking at propagation around the body, and we're looking at RSSI, but we're using a smartphone in this case and an RSSI logging app to log the signal strength, and then we can compare it. So you can see that whenever we place the Thunderboard on the upper arm, we then would place the phone in different locations around the body, different pockets, different orientations, and then we can measure the RSSI. And we here, just from this one sample of the results, we have a similar outcome to the previous measurement, and we can see approximately a 16 dB difference in RSSI. In this case, transmitting from the upper arm to the back pocket. And again, this is because of this optimized on-body radiation mode we produce. The next example, we're not looking at propagation on the same body, we're looking at off-body performance. And in this example, we're just looking to see how far we can go with using standard off-the-shelf Bluetooth SoCs in a wearable device. And we're focusing on getting maximum range. So we're using the very popular NRF52 Bluetooth SoC, and we're also using front-end module the NRF 21540. And again, we're using coded PHY just to see how far we can go. And on this board, we have both a body wave antenna and a printed Inverta F antenna. And through the RF switch in the FEM, we're able to switch what antenna is active. And this way we compare the RSSI received from each antenna during the same measurement, so that's fair. In tests where we're testing off-body performance, we would use, like a dev board as the receiver, maybe using the integrated antenna built into that dev board. But if it's not so good, we could connect up an external antenna and conduct these measurements. And then we would also conduct the measurements with the receiver in multiple orientations. And this would be just to analyze what effect receiver polarization has with this kind of wearable application. So if we're just comparing signal strength versus orientation, test subject would just walk to a known distance and then rotate on the spot. And then we can see what that does to signal strength, and we can see what different, what kind of knowledge you would get from the non-line of sight case. But now we want to look at how far we can go. So now it's just a case of walking from the receiver until no packets can be detected in whatever time frame we dictated. So we conducted these measurements on a beach in Northern Ireland because we needed a very long test range. And this plot shows the non-line of sight performance. This is when the device is placed on the chest and you're just walking away from the receiver. And you can see that the body wave antenna had a much better performance than the PIFA, given nearly 300 meters of extra range. So we tested a range of other orientations, but this was the best one. So this was when the test subject with me was side facing to the receiver. And in this configuration, we were able to get a range of about 1.59 kilometers. And that involved crab walking 1.59 kilometers. So it's not a very pleasant experiment. And that's just really how far we were wanting to push it to these kind of levels. So yeah, that's just a few examples. I just want to plug some of the work we're doing here in AntennaWare. So we have a number of body wave antennas in production that we sell in these frequencies shown, with a few more planned for release later this year, such as a few more UWB variants, some sub-gigahertz variants. But although the core technology can be adapted really for any frequency, so we're happy to take any recommendations on where we should go next. The good thing is the core body wave technology works at any frequency. It's just a matter of scaling the antenna for that frequency, and we can create multi-band variants also. But that non-line of sight performance you've seen, it's still exhibited in all these frequency bands that we've been looking at. We've also found as we go up in frequency for close fitting wearables, our performance relative to standard antennas is increasing. And this is due to what Gareth was showing, the increasing conductivity of tissue, and also the body being electrically larger at these higher frequencies and therefore more of an obstruction. And this sort of exacerbates this non-line of sight issue. So that's the end of our presentation. And yeah, we'd be happy to take any questions that we have now.
Thank you, Gareth, and thank you, Matt. Absolutely compelling content. And I would like to thank both of you for everything you've done, and Sarah as well. Almost overwhelming, the amount of people that have attended this. And we're going to have to just take a very quick snapshot of the many questions that have come in. And we'll start with the first one. This is from somebody, due to GDPR issues, I'm not able to say who they are or where they're from, but I can say they're from England. Gareth, what are the sizes of the UWB antennas?
Johnny, the UWB band runs from about 3 to 10 gigahertz. The popular bands that we're looking at antennas where we've got down to 5 by 5 by 2 millimeters, so 5 by 5 XY dimensions and 2 millimeters in height. But obviously the antennas, it's a trade-off, and we're more than comfortable to optimize that for different form factors. But that's where we're at with the product at the minute. So the lower bands will have slightly larger antennas, but that's where we're at with some of the higher bands in UWB.
Beautiful, beautiful. Another question coming in. For the chip antennas versus body wave antenna, what are the standoff differences from the PCB? Does this have a major effect on antenna performance? Again, Gareth.
Yeah, so if you mean the PCB antenna separation, for printed antenna, you're going to be printed right on the PCB. The body wave then sits right on top of the ground plane, so we're not really looking at standoff distances. If you're thinking about the height of the antenna, it's a chip antenna that sits on top of that board, and across the product range we have different heights, but again, that's something that can be optimized. What is probably more important is the PCB to body spacing. That's very critical. So if you put a printed antenna very close to the body, that's really going to have the biggest effect on your performance.
Gareth, good man, good man. Rattling through them now. Here's one for Matt. For the body blocking issue, what would the drawback be for adopting multiple antennas into the system if possible? And that's from somebody in California.
Okay, I mean, that is one way to get around the problem, but it's probably not the most elegant or efficient way. I mean, you're greatly increasing, your system complexity. You're really relying on making sure that your antennas are in, where you would see the non-line of sight zone to be. So having a multi-antenna system will get you around the problem, but it'll increase the the complexity, the BOM cost, the power consumption of the system. If you kind of do things these ways, so that's why we sort of tried to get around this issue by optimizing the antenna performance rather than having to rely on multiple antennas.
Beautiful, beautiful, Matt. You really are the oracle. Not a bother, not a bother. This is one in from, and I'm going to breach GDPR here. This is from Jackie Green, who would know an awful lot about antennas. And her question is, what frequency was the test with multiple sensors walking around? Also, did speed of walking affect the results? And I think that's one for you, Gareth, if you know.
Yeah, Jackie, if you're talking about the early research stuff where you've probably seen me in a wetsuit with a lot of sensors on it, certainly walking around did affect the results, but probably not so much the antenna results. Well, it does if you use printed antennas because the antenna body spacing is varying quite a bit as the person moves. But if you use something that is insensitive to that antenna body spacing, like the body wave, you'd see less of effect of the impedance and efficiency variation. In terms of the speed of walking and the way the person walks is certainly going to have a massive effect if you're in a multipath environment, and the depth of the fades and the frequency of those fades will be largely affected by the speed of walking versus stationary.
Here's another one, and I'm going to ask Matt to answer this one because this is all about his tests on the beach on the North Coast. For walkout tests on beach, did you adjust transmitter output power to accommodate for regularity power limits? That's an excellent question.
Trying to think what we'd set it up. So we were basically looking to see how far we could go. So we put the transmission power up, I think, nearly as high as the front end module could go. So yeah, it's within regulatory limits. And I think, I can't remember what the exact power was, but it was within what can be used. The other thing we were doing was we were using the coded PHY as well, just to try and really hit that range. So it wasn't just through the antenna performance and transmission power, we also had a coded PHY in there. And that's how we were able to get that distance.
Right, awesome. I remember that day very well. We were very excited. We actually thought about an application in the Guinness Book of Records for transmission, but Sarah, being our handbrake, ruled that out. Here's another one, probably for you, Gareth, because this is your pet subject. Do you sell the phantom test bed you have developed?
Where's that question come from?
From Italy.
I've been asked this. The reason I'm laughing is that I've been asked this a few times across my career. I never want to have to build some of these again, but I built it for a reason. I built it that I wanted a test bed that was variable and represented a broader range of people than one or two people I had access to in my lab. I guess the real answer is that if you take an antenna like the body wave or something, you don't need to do those types of tests that I spent years doing and building test beds for. But the short answer is no, I don't sell those test beds. I have no plan to.
More questions coming in. I'm trying to think on the hoof here a little bit on the best order of them. This is one for Matt. I'm going to ask Matt on this one. Would you be able to share a CSV file, black box containing the data of your chip antenna at 2.4K?
Yes, yeah, we do have that. Yeah, we can share that.
It's okay. Well, it sounds quite quick, that much.
We-
I have to
we've
be
got that
Have you tested the antenna performance when the ground plane is between the body and the antenna facing to the body?
Yeah, we have. So I mean, it depends on what your use case is. Obviously, sometimes you can't always have the ground plane facing the body, but we found that if you invert it, you do have a slight reduction in the gain found in that direct kind of line of sight direction. But what it actually does is it helps improve the performance in directions sort of around the body. It can produce more of a detuning effect and lower the radiation efficiency slightly. But if you're at the sort of higher frequencies where the near field of the antenna is closer to the antenna, it's less pronounced if there's a good spacing. But it has something we've looked at, and we've looked at it extensively for the 2.4 gig antennas and UWB antennas. It's not been a major issue.
Right. Gareth, I'm going to leave this one with you to pick the bones out of it. Do you find the antenna performance gains vary with the RF transmitter method, i.e. continuous wave versus pulse, or narrow band signal versus wide band? And okay, that's been bounced over to Matt. Controversial.
To be honest, the only methods that we've used has been sort of these kind of narrowband radio techniques. So I mean, using standalone passive antenna measurements in chambers, that's how we would test standalone antennas. For the kind of narrowband radios, I would say Bluetooth. We've a lot of experience with that, but going to UWB and those kind of systems, we've generally seen no difference in the performance of the antenna. We're getting, when we go from the anechoic chambers to going into practice in the field to do field measurements, we're still getting the same kind of predicted ranges that we're seeing from simulations in our chamber measurements through to the implemented system. So no, there's not been any massive variation between the feeding method. No.
I'm probably moving towards the last question here, and probably enough. This is from Stevie in Ballymoney. Gareth, what's the optimum frequency for wearable communications? Oh, I already asked that one.
No, yeah. I could go down a wormhole in this. Johnny, there's certainly popular frequencies, and I think the frequencies that are selected are more around interoperability and what handset manufacturers have used for the frequencies. In my experience, do not think there's a golden bullet or a silver bullet in terms of selecting the right frequency. Obviously, if your physical dimensions allow it, going to lower frequencies is beneficial, but as the world moves up in frequency and handsets, we want to communicate with handsets. I don't think we have much control over the frequency. So there are massive benefits in terms of size and populating the board when we start to move up into the UWB band. So there is, in terms of the physics, there have been a few frequencies pushed around there at the minute, but I've never seen them being used.
Okay, I think that's us coming to the end of our first webinar. Again, thank you, Sarah. Thank you, Matt. Thank you, Gareth, for sweating to make this such a good experience. And many thanks to the attendees who listened in to try and walk away with some more information around antenna design. We will send out a follow-up email in the next 24 to 48 hours with a recording of the webinar. And all being well, this is the first of many. So it feels like a very hot subject for wearables and for wireless in general, how to overcome body blocking. And so with that, thank you very much.